So we see up on the board right now the diagram of the homework question that we had last night. We're trying to add together these 5 vectors, 200 meters to the south, 100 meters to the east, 100 meters to the north, 400 meters, and another 100 meters to the east. We can draw the resultant vector in here, or the vector that represents the sum of these vectors pretty easily, actually. It goes from here to here, from start to finish. That's a correct vector diagram. All those black vectors are drawn from front to back, front to back, front to back, and so on. Except that blue one is drawn from back to front. It's okay. It's the resultant vector. It's supposed to be drawn backwards. It's supposed to be drawn from back to front. Now, it's a correct vector diagram, but it doesn't really help me a whole lot in its current form. What I've got to do is take components of each vector and add those components up, so that in the end, I can get one single right-angled triangle. I can't solve this question without a right-angled triangle. This is not even close to a right-angled triangle. Now, the first thing that I really want to do here, actually, before I separate anything or before I draw a right-angled triangle, is to get rid of this funny angle. I don't like funny angles. Okay, it's 30 degrees. I don't like to see 30 degrees there. We want to get rid of that and turn that into basically 90 degrees. So let's draw that vector off to the side over here. We've got 400 meters and an angle of 30 degrees right here. Let's complete that triangle. Remember, this is not the whole problem. This is only that one vector that we're replacing now with an x and a y vector. Now, the x side of this triangle is which side? The opposite, adjacent, or hypotenuse? It's the adjacent side, right? So we're going to use the cosine function in order to find that. Cosine 30 degrees is equal to x, the adjacent side, over 400. What does x equal there? 400 cos 30. Travis? Pardon me? Can you say that again? Okay, thank you. 346.4 meters. Now we're going to find the y component, say sine 30 for that, because it's opposite over hypotenuse. And that one equals, I believe, 200 meters. Let's draw a little thing around this, just reminding us that it's kind of an aside. It's not really part of the main part of the question here. Now we go to the main part of the question. Now we go to our x and y components of each vector. Real quickly, the x component of 200 is none, 0. I'm going to write that down. Some people will choose to just leave that off and not write it out. Okay, I want to write it out just so that I can keep structure here. Okay, structure is important. Okay, structure helps us through things if we make a mistake. Okay, I want to write down 0. I want to write down 100. I want to write down 0. I want to write down whatever each of them are, so that if I have a mistake here somewhere, I can go back and find my mistake easier. What's the x component of that fourth one, by the way? It's not 400, right? We're never going to use that 400 again. It's done. It doesn't exist anymore. What's the x component of that 400 that we're going to use? 346.4. That's why we did this, right? That's why we did what's in green over here. And then the x component of the last one is 100. We add those up, we end up getting 546.4. Now, y components. The y component of the first one is negative 200. 0 for this one. Positive 100 for the third one. What about for the fourth one? That 400 meter vector, what's the y component of that one? How much of that is going up, Brendan? 200, good. And then finally, the y component of the fifth one is 0. We add those up, we end up getting positive 100 meters. Now, some of you stopped there. Now, when you stopped there on your homework, I don't think it's because you were lazy and didn't want to finish. I think if you got this far, I think you legitimately wanted to do the question. I think some of you got to this point and thought you were done. When we said add these vectors together, you thought, well, we just added these. We just did addition. Yes, we did do addition, but we still haven't added these vectors together. We've added components of these vectors together. How do we finish this off? Well, to finish it off, we've got to draw a new triangle. 546.4 meters to the right, 100 meters up, and then our resultant vector is going to be drawn right here from start to finish. So we're replacing that big diagram with 5 vectors plus our resultant into a smaller diagram with 2 vectors and a resultant. And this was much better because now we have a right angled triangle. R can be found by taking the square root of 546.4 squared plus 100 squared. And theta can be found, as we know from the last couple of days, by the inverse tan function of opposite over adjacent. Can you tell me which side is the opposite side of this triangle? Is it 546 or is it 100? Which one's opposite to that angle? Fraser? Good. So let's calculate each of those now. For R, we end up getting 555. And for theta, we end up getting 10.4 degrees. Does that make sense? Yep. So you can't do it the other way? Oh, you mean like the 100 then the 546? No, you can. Yes, you can do it that way. Good question just asked. Guys, take a look up here, please. Up here now, please. Good question just asked. Can we do it the other way? Let's say we had drawn 100, then 546. Can we do it that way? Yes, absolutely we can do it that way. As long as the vectors are drawn front to back, it's okay to draw it that way. Now that resultant vector would mathematically work out to be the same length, 555 meters. But the angle wouldn't work out to be 10.4 degrees. The angle would work out to be 79.6 degrees. But that would also be correct. Okay? So here we got 79.6 degrees. Now I do want to give you another example for you to work on here at your desks in just a moment here. But before I do that, I want to teach you one more small thing that we're going to add to this. And that is our frame of reference. What does this 10.4 mean? What does the 79.6 mean? I gave you a little bit of an analogy yesterday or the other day to show you how you can have 2 different answers for direction that are correct. I stood right here and I said I'm 2 meters in front, or 2 meters, yes, 2 meters in front of Daniel, and I'm 2 meters behind that day Olivia. Okay, both of those mean exactly the same thing. Both of those describe my position very well. But notice I didn't just say 2 meters and 2 meters. I said 2 meters in front or 2 meters behind. So I had a frame of reference. Okay, it was where am I relative to Daniel? Where am I relative to Olivia? In front or behind? This doesn't say that. This gives me the equivalent of the 2 meters, right? It gives me the number, but it doesn't tell me relative to what? Relative to Daniel or relative to Olivia? So I have to have a way of describing that. The way I'm going to describe that is using a system where we use, where we describe it in terms of how far north it is, or how far west it is, or how far south it is, or how far east it is, relative to another direction, north, south, east, west. So this one, we're going to actually say is 10.4 degrees north of east. Why do we say that? Well, because you can see that resultant vector is measured from the eastern axis, from the positive x-axis. Or does it go from that? North from that, right? It's north of east. It's north above east. Okay, this one would be 79.6 degrees east of north, because the angle is measured from the north axis right here, but it goes east of that. So it's east of north. Now, another way to think of that is this. In order to get from here to here, we went east, then we went north. We went north after east, or we went north of east. In this one, we said we're going north and east. We went east after we went north, or we went east of north. Does that make sense? Now you can see that those two numbers, although they look different, 10.4 degrees north of east, 79.6 degrees east of north, it's not just two numbers that are different. Okay? I'm 1 meter behind Olivia. I'm 3 meters in front of Daniel. It's not like saying 1 and 3 are the same thing, right? 1 and 3 don't appear to be the same thing. 1 behind Olivia and 3 in front of Daniel can absolutely be the same thing. 10.4 degrees north of east, 79.6 degrees east of north, right? Let's give you another one of these problems to work out at your desks here, okay? You guys did a good job of these last night, okay, but there were a few people with some troubles with them. So let's see if we can eliminate those troubles right now in this question. If we can't, then we'll give you another one beyond that. I'll draw this one out again for you just to save yourself the bother of doing that. Okay, I want you to find the resultant vector of all these vectors. In other words, I want you to find the sum of all these vectors. Okay, let's go at it. Let's take a look at this question now. There is only one Rutger. There is only one Rutger, but that's not what I meant. There is only one. Yes, there is. But I meant there's only, I don't know what I meant. What did I mean? I lost my train of thought there. There is only one funny vector here, funny angle here. Turn around. We can draw a resultant vector from start to finish down here. Now that looks like it's straight down, but I haven't drawn this to scale, so it may not be supposed to be straight down. That's not a big deal. Okay, if it's not perfect, it's not a big deal. We got to get rid of that funny vector first, that funny angle, that 30 degrees, 50 meters. So let's do that over here. Here's my 30 degrees. Here's my 50 meters. This is the x side. This is the y side. We can calculate the x side using which trig function? X is the adjacent side of the triangle. So I'm going to use which trig function to find that adjacent side? Yep, cos, right? It's so, ka, toa. Cosine is adjacent over hypotenuse. Cosine 30 degrees is equal to, oops, 30 degrees it should be, is equal to adjacent over the hypotenuse. X ends up being equal to 43.3 meters. Now the y component, we're going to use the sine function for that since it's the opposite side. Sine is equal to opposite over hypotenuse. That's y over 50. Y ends up being equal to 25. Okay, there's my little aside. Now let's go to the meat of this question. The x and y components of all the vectors. Let's say for the first one, the x component is 100. For the second one, the x component is 0. Good. For the third one, it's 150, right? Good. Negative 150. Thank you. For the fourth one, it's 0. And for the fifth one, this one that was at 30 degrees, 50 meters, which no longer exists, by the way. The fifth one is going to be what? 43.3, positive or negative? Or a positive or negative 43.3? Positive because it's going, yeah, it's going to the right, going east or going to the right. Good. So it's going to be positive 43.3. Let's add these up. We end up getting, I think, 6.7. Is that right? Or negative 6.7. Is that right? Let's do the y components. The y component of the first one is 0. Then we have neg 50. Then we have 0. Then we have neg 100. And then we have what for the last one? Not 50. That's what's 25, right? Or is it negative 25? Add those up, we get negative 175. Let's combine those. We got 6.7 to the left. We have 175 down. The resultant vector will be drawn from start to finish, and the angle is always going to be drawn at the very beginning there. When you solve for r using the Pythagorean theorem there, square root of 175 squared plus 6.7 squared, we end up getting 175 point something, right? Well, this should really be rounded to 2 digits, because if you go back to our original data, we had 50 meters twice, and we had 30 degrees once. Okay, we had 2 digits 3 times. We're going to round that to 1.8 times 10 to the 2 meters. Theta is equal to the inverse tan function of opposite over adjacent. That's 175 over 6.7. Who's got that angle there? 88 degrees? Okay, so this would be 88 degrees. Well, we went west, then south. So it would be south after west, or south of west. Now, had you drawn the vector diagram like this, which you could have, then you would have gotten an angle of 12 degrees right here, but it wouldn't be 12 degrees south of west, it would be 12 degrees west of south. Both would be correct answers, and both of them would be accepted as correct on a test or a quiz. Okay? You guys feel okay about that? Okay. Let me give you one more question to work on for homework. Okay? You will also have a quiz on Monday, but your quiz on Monday on this stuff will not involve funny angles. Okay, a quiz on Monday will involve right angles. Okay, it may involve 5 or 6 vectors, but they'll all be right angles. Okay, a little bit later on in the week, maybe Tuesday or Wednesday, we'll do a quiz with some funny angles here. Once we've had a chance to check over that question that I'm giving you for homework this weekend. Okay? All right, last one. Hopefully this is the last question on this stuff that I give you, okay? As long as we do okay with it this weekend, then it will be. There we go. Oh, we threw in 2 funny angles this time. Does that make it harder? Makes it take longer, right? For sure it makes it take longer, but it doesn't make it any harder as long as you can deal with the funny angles. All right, see what we can do with that. Work on it for the next couple minutes here in class, and then finish it up for homework this weekend, please.